www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Let's begin. This is lecture 25 for Schottky diode. And Schottky diode is like a PN junction diode, but historically and also for many practical reasons, it is something, and also for pedagogical reasons, this is a very powerful device, and I want to introduce you of how it works. Now, I will start by talking about the importance of metal semiconductor junctions. Now, metal semiconductor, the PN junction we talked about so far, what was it? Semiconductor junction, right? It could be same semiconductor homo junctions or different. Let's say germanium on one side, silicon in another. So that it could be, but here definitely it's different, metal and semiconductor, and I want to explain how it differs. We'll again go through the same process. We'll first draw the band diagram. Any new device you have, first thing, draw band diagram. So we'll do that. We'll also explain why the things that I have told you so far about doesn't really apply when you want to calculate current in a heterostructure. But what I'm going to tell you today, that is going to complete the picture in terms of how to calculate current. If you know these three processes, then any other device that comes in your lifetime about various carriers, various devices, you should be able to handle. And then I'll conclude. Now, metal semiconductor diode is actually a very simple diode, in one of the oldest diodes that people know about. One side is this green semiconductor. It could be N or P doped, but in this case, let's say this is N doped because Nd is the donor. And the red are the metal contacts. Now, many times historically, people didn't put a metal down, but rather if you take any wire, and then touch it on a semiconductor, then that becomes a metal semiconductor diode. So in the old days, the first transistors, the transatlantic transmission and all those are all metal semiconductor diode. The first bipolar junction transistor, I'm going to say in a second, that was really metal semiconductor diode, not the thing that you read in your book. What we read in our book is very different from what was invented in 1947, and most people don't understand that. So I'm going to explain to you that. Now, most of the time, again, we'll be doing a one-dimensional cut and look at the one-dimensional flow just for simplicity. But as you realize that when you have a wire touching a two-dimensional or three-dimensional semiconductor, a chunk of material, the current will come through that point and spread out. So that's a little bit more complicated, but for the time being, we'll ignore that complexity. The symbols, again, the symbols are very similar to the diode, but you will recognize that there is this extra wings sitting on the corner that tells you about that this is a metal semiconductor diode they are talking about. Most of the output characteristics will be very similar to the PN junction, but the physics is very different. Okay, it has a lot of applications, metal semiconductor diode. For example, if you, in many, as I said, in radio transmission, in other cases, in older days, people used to use these metal semiconductor junctions to demodulate, extract back the carrier signal from the signal from the carrier. But there are many others. For example, this is a historical replica of the detectors of signals. You can see the wire, right? Do you see that wire hanging from that sort of the cantilever? And the semiconductor is like a paste. The yellow paste, lead sulfide is a yellow paste. And that's in the early days, that's what people used to do as a diode. That's the diode actually. Now, there are, of course, this first original bipolar transistor, that turns out to be a metal semiconductor metal transistor. It is not the classical transistor that you study. And I will explain, and you will do a homework on this, that how the original transistor worked. So that's already in your homework. Then people talk about carbon nanotube transistors that you may have heard about. Do you see that there is looks like a bridge between this, a single line bridge between the two sides. The two sides, the two islands are contacts. These are metal contacts, and the long wire is a semiconductor, carbon nanotube. So That's something that's very important. People work about it all the time, metal semiconductor junction. And then, of course, the STM tip. Anytime you have a metallic STM, scanning tunneling microscope, where you put it down and drag it over a surface to see the surface topology or the surface electronic property, it is essentially a metal semiconductor junction, because the tip is often a metal and the base is semiconductor. So, of course, the physics is very similar. So, this is actually what you are going to learn, has a wide range of applications. So, the yellow paste, as I said, this is called gelena or lead sulfide type paste, and for many materials for many years the people have used it as a semiconducting material. So, let's start with equilibrium band diagram. Now, equilibrium band diagram, what I want you to notice, the reason I am putting up this topic map over and over again is when you study for this course, or you want to really capture what you have learned in this course, you should go back and see that everything I'm doing under the equilibrium column is always the same. I'm always following the 4 rules, and I will never break from the 4 rules, and I'll always get the right answer. And similarly for DC, you will see that I will be doing a same set of things over and over again. AC, large signal, same. Anytime I see large signal, you will see I'm doing charge control. So I want you to follow the pattern, because these are, of course, devices people already know. When you go for work, they will not be asking you to do a MOSFET analysis. They will ask you to do something else. And again, if you know the pattern, you'll always be okay. So the first thing is that anytime I want to do an equilibrium, I'll have to solve that equation, right? That's the Poisson equation. And this graphical solution is called this band diagram. That's the graphical solution of the Poisson equation. I'll also have to solve these equations. But what I'm going to show you, that I have to do something special about solving this equation, because this may not really directly apply to metal semiconductor junction. I'll explain to you in a little bit why. Okay, what is the rules? What are the rules for drawing a band diagram? First, draw a quasi-Fermi level. So a Fermi level flat across this region, because the property of equilibrium, no matter what happens, is always that the Fermi level is flat from one side to the other side of the junction, because had there been a gradient, there would have been a current, right? You remember that the gradient of quasi-Fermi level tells you how much current there is. No current in equilibrium, no net current. So therefore it's flat. The next thing is to draw the conduction and a valence band of the respective side. Now this is a metal. In a metal, Fermi level is above the conduction band in a given conduction, one of the bands, inside one of the bands. And so therefore, you see the band gap is right there, the blue. But the Fermi level is like a degenerate semiconductor, as if. And so the Fermi level is inside one of the bands. Why is it? Do you remember? Because it has generally odd number of electrons. So therefore, in metal generally, the Fermi level is half full in one of those bands. Okay, so that's fine. Now what about the semiconductor? Oh, by the way, so there's a phi sub m is a metal work function from the Fermi level. How much energy does it take for an electron to go out and get free? And so that is the amount of energy, phi sub m. So you can draw that immediately, because you know what the Fermi level is, and then you can just draw the dotted line that gives you the vacuum level. Now let's come to the other side, for the semiconductor side. This is a N-type semiconductor, I assumed, right? I assumed an N-type semiconductor. So I should draw that line first, because this is close to the conduction band. And with using the band gap of that material, whatever that material is, then I draw the EV. So that gives me the band gap. Now the next step is that I have the chi. I'm sorry. So this from EC to the vacuum level, that is chi. That symbol I'll put it down in a second. But that is chi. So you first have to do the chi to get the dotted line. And the blue and the red region that you see with the vacuum level, that is essentially taking the right hand dotted lines and the left hand side dotted lines for the vacuum level and connect it up continuously. It doesn't matter how you draw it. Just draw it anything, but it must be continuous. So you do that, and the next rule is that once you have that thing from the blue region, you copy it down and you copy that down. That's one side. And copy this down and copy that down, because equal to the band gap, remember, and the blue side band gap and the red side band gap need not be the same, right? Need not be the same. And so then you connect it up. That's your band diagram. That's the device. That's really a metal semiconductor junction diode. You can see the electrons from the EC side will go over the barrier and get to the blue side and get relaxed down to phi sub m for the energy. We should talk about the transport in a second. But that's the answer. That's the band diagram. Now, in general, in the band diagram, whatever the band diagram is, and I'm going to show you that in general, you have seen that the blue region I have drawn, the drop in the blue region, I have dropped it small, right, here. And red, I have bent it up a little bit more. Now, in principle, there's no reason why I should do that a priori. But what I am asking you to believe or see, and I'm going to prove you this in a second, that in a junction, you know that charge on the left hand side must be equal to the charge on the right hand side. So if the left hand side, this relationship we have seen before, right? Na, which is the acceptor, xp, which is the charge on the left hand side for a PN junction, and Dn and Xn is the charge on the right hand side. So the metal is degenerate, right? Huge amount of charge. So therefore, quote unquote Na is very large. If it is very large, then you can see xp has to be minuscule, right? It has to be minuscule because the total amount of charge on left and right must be the same. If it is minuscule, in fact, it turns out to be so minuscule that in most of the cases, you will see the blue in the books. The blue band bending is not even shown in the books because it's so minuscule, like maybe 2 to 5 angstrom at most on one side. On the other side, hundreds of angstroms, right? 10 to the power 17 on one side, 10 to the power, few times 10 to the power 20 on the other side, on the metal side. So in your textbook, when you look at it, you will see that they have just drawn a straight line. But actually, this is what they have done. They haven't just simply told you. So that's why you make that negligible and don't draw the band diagram this way. That's the kite. Okay. What is my first thing do I do after I finish drawing the band diagram? QVBI, the built-in potential. That's the first thing I do. And the built-in potential, remember, only thing I care about, leftmost part of the material device and rightmost. You may have 273 devices or 273 junctions. But only thing that you care about for VBI, junction of the material on the leftmost side, number 1, and the material on the rightmost side, 273. So that's the only thing you care about. In between, it can do whatever it wants. VBI doesn't care. So this is how it works. So for example, how will you do the VBI? You know that, right? Quasi-Fermi level is flat. All I have to do is to make sure that on left-hand side and right-hand side, they reach to the same level. So for example, this, do you agree? Delta is how far the EC is different from EF. Chi, of course, you can see that's the vacuum level work function, and then Q VBI is the extra built-in potential. That's what you have on the left-hand side, and equal to phi sub m on the right-hand side. That's it. So in this case, these values phi sub m, chi, these are given from tables. So we have tables that tell you that if it is copper, this much phi sub m. If it is aluminum, then this much phi sub m. So this value you just read off from a book. And chi, of course, silicon, germanium, each has different amount of chi. That's fine. Delta, how will you know delta? Doping, right? The doping tells you how close it is, close to the conduction band. So you can see QVBI is known. QVBI is that way. By the way, this chi sub m, phi sub m minus chi, you see that's really effectively equal to the barrier. That's the from the green region to all the way to the top of the conduction band. So that's the barrier. They will call it phi sub b. That's the barrier height. So barrier height is different for each pair of materials, right? And then you can see this delta. Delta is given by ND over NC, given by that factor. Now this is only true if it is a non-degenerate semiconductor, right? If it is degenerately doped on the right hand side, then I'll have to write a more complicated equation for the value of delta, but that you knew, so don't worry about this one. I know QVBI, the built-in voltage now for this, and this is a general trick. You can do it for any devices that you want, no new things. So now I want to do a few more things. Let's see, in general, what you want to do is, again, you have a depletion charge. The blue is the depleted charge on the N side. Why there's depletion? Because there's band bending and the charges have been pushed away. And the red one that I have shown you is the charge on the metal side. And you can see it's huge, and therefore its width is very small. Again, you can do this in the book. There are this integration. You start from the left-hand side, gradually come and gradually integrate through the red region, which increases the electric field, and then gradually go through the blue region, which takes away from the electric field, and essentially you'll have it on the right-hand side, extreme right-hand side again, the electric field is 0. Again, the same thing, PN junction, there's nothing funny here. But you can see, because the red region is so tiny and skinny, therefore, the electric field, when you integrate it, it almost looks like a jump in here, because it, in a small distance, it gives a lot of integrated area under the curve. Therefore, it jumps up, and gradually on the right-hand side and the blue side also, it will gradually take away the electric field, the red region generated. Eventually, it will make it equal to 0. So you can calculate the maximum electric field, can you not? Because if you knew the donor density, and somehow if you knew Xn, how much it has got depleted, then you divide by the epsilon, then you are done. But of course, you don't know Xn. So that I'll have to calculate somehow. By the way, so after you are done here, then what you will do is you will integrate this electric field to get the potential, right? And do you now realize why there is the potential starts from almost close to 0? Because look at that curve. If you integrate that skinny triangle on the left-hand side of 0, that has almost no area. It has a lot of ordinate, but no area. So therefore, the blue curve on the bottom, you do not get any contribution to the potential drop. And then, of course, on the right-hand side, the potential quickly picks up. And this potential is VBI on the right-hand side, right? That's what VBI is. And so you can calculate Emax and Xn divided by 2, area under the triangle over there, that's equal to phi sub max or equal to VBI. And then once you have this, you flip it over, right? And if you flip it over, then that's the band diagram that you will see that is often drawn in your textbook. Okay, so let me go through this a simple calculation to show you how it works. Exactly the same as PN junction diode. I really don't have to do much. Look at this. So at E equals 0 plus, you have ND and Xn, and E at 0 minus, you have N metallic, whatever that number is, and XP is whatever the depletion on the metallic side is. The thing is that I don't have to know that. I'll show you in a second. So in general, you can write, because the charge has to be the same, you can write NdXn equal to Np, N sub p, Xp. And similarly for QVBI, it's the area under the triangle. You write it the same way, right? E at 0 minus Xn divided by 2 and 0 plus Xp divided by 2. And you will have this squared term on Xn squared and Xp squared. Now you know QVBI, right? You know QVBI. Nm, well, you don't know. In a PN junction, I knew what Na and Nd was. So I will not be able to solve this problem in general. But fortunately, it turns out that Nm is so large that Xp is negligible. As a result, I'll be able to drop this term and then from QVBI calculate Xn and not use the top equation at all. You see, that's the trick. That's the extra trick that you have to do. And so from here, what I am going to say that that Nm is very large. If Nm is very large, then do you see how the standard p-n junction equation becomes independent of Nm? Do you see that? If Nm is very large compared to Nd, then Nd I drop, and I have Nm on the top, Nm on the bottom. That gets cancelled, and I have nothing on the right hand side for Nm. That makes sense, right? Because it is so large that in that case the tiny region doesn't really make much difference. And you can do the xp, but you can see this time it will be 0, close to 0. Do you see that again? Because n sub m is much greater than Nd. So I'm going to drop that. But now n sub m is in the denominator. And when you have a very large value for that, it's like a one-sided junction. So that goes away. So mathematically, it's telling me exactly what I have felt intuitively, that this should be the answer. Okay, so now I have told you about this band diagram equilibrium. Now the DC current flowing through this junction is a little complicated. Not complicated conceptually, but it's a little different. I cannot use directly this drift diffusion equation that I have derived in the first 5 weeks of class. Anytime I have a discontinuity in the conduction band, a heterojunction, right, or in the valence band, then I have to use a slightly different theory, which is very simple, called a thermionic emission theory. So anytime you see a discontinuity in the conduction band on any material, any device, then you have to use this particular way of viewing things, as I will explain. So I'm talking about now the DC and the Schottky barrier. Now what I just said is that this way will not work. Now this theory only works generally when you have a continuous conduction band or a continuous valence band. In that case that works. When you do not have that, then we will try to do things in a slightly different way, but actually simpler than p-n junction. You will see it takes just a few minutes to explain how it works, but you have to pay attention. This is the band diagram in equilibrium. I shouldn't have to draw that again, right? So you know that. I just drew it a few seconds ago. QVBI, you realize. And for this material, I have just grounded the metal side. So you can see that's the ground on the left-hand square, little square, that's the ground. You always need to ground a terminal of a device. If you don't ground it, then you cannot draw a band diagram. Everything will be confusing. So I could ground right-hand side or left-hand side. I decided to ground the left-hand side. Anything is fine. You can do the other way. Now, do you realize that this is a bias device and it's a forward bias device? See the rules, whether I have followed the rules. I've grounded, of course, the left-hand side, one of the corners, and on the right-hand side, I have applied a voltage. Now, a priori, I don't know whether it's a forward or a reverse bias, but at least given that this voltage is negative, let's say, in that case, what I have done is that I have split the Fermi level, right? So the Fermi level is now, the top one is Fn, and the difference between EC and Fn, that has remained the same because carrier concentration in the bulk region cannot change. So I have that. I also have the F sub P, quote unquote F sub P, because it's really F sub metal, that also continuous, but equal to where it was before. And do you see where I have stopped? I have stopped on the other side of the junction, and I have not continued any further. How to continue any further? That's your homework problem. There's a homework problem. You will see that that's how I show that where I stop beyond that point. If you wanted to go on, then how will you draw the quasi-Fermi level? That's one of your homework problems. But other than that, I have followed the rules I have told you before about p-n junction, so I haven't violated anything. Now, the reason, what voltage, this I said it's negative because only with negative voltage, the electron EC will move up. Electrons don't like negative voltage, sort of. That's how to remember. And it always moves up. And as a result, there will be an electron current flow through that structure from the right side to the left side, because the barrier is now a little bit lower, right? QVBI was the original barrier. Now it's a little bit lower. So more current will go from this side to the other side. The current from the green side to, or from the metal side to the semiconductor, that almost remains the same, because you see this wall it has to scale, or the barrier it has to go, is the same on both sides, from going from the metal to semiconductor. But from semiconductor to metal, you see the wall is a little bit lower, effectively a little bit lower. And do you realize that this is a reverse bias? Because I have applied a positive bias on the N side, and as a result, I have pushed down the quasi-Fermi level for the electrons while keeping the metal for quasi-Fermi level almost the same. Now, you will not see this type of thing in the textbook, and you see in the, because they essentially don't draw it for many different reasons, but you have to follow the same rules so that you don't get confused. Okay. Do you see on the other side of the junction, I do the same thing, same rules, I follow the same rules. If you don't follow the same rules, then of course you cannot, if you want to do the recombination generation events and other things, until you draw them properly, you cannot really compute properly. Okay, so that's the reverse bias. So this I will not have to tell you at all, right? When you apply a bias, then this QVBI, whatever was the QVBI, you can apply a bias with a VA, that gets reduced, and in a forward bias. In the reverse bias case, when you apply a positive thing, then the depletion region becomes much wider, right? That's the reverse bias side. XP was 0 to begin with, so 0 I don't really want to modify with a VA, that remains 0. So there is very little band bending on the metal side. Okay. So now I want to calculate a few currents, but first thing I want you to realize that whatever you saw in the PN junction semiconductor, if you look at a metal semiconductor junction, you will almost see the same things. Same thing. You will see that there is this region 1, 2, 3. Remember this 1, 2 diffusion controlled, ambipolar, and then there is series resistance drop. You will see the same thing. In some of the diodes, if it has a lot of defects in the junction, then you will see this number 6 and 7, the ECE606 type tunneling, and also this trap assisted recombination at low voltage that has half the slope, right? Do you remember half the slope? Because of the electrons holes coming in the junction and recombining. So that regions are exactly the same, exactly the same. Physics is different, but the features are essentially exactly the same. And in the reverse bias is very similar. You'll again see a region 4 and 5. 4 region is as the depletion is getting larger and larger with reverse bias. Then there is this generation current that goes with a square root of V, right? Square root of V is how far the depletion changes. And so you see region 4. Region 5, you'll have impact ionization. If you apply large enough bias, then electrons will come in, they will multiply within the junction and huge amount of current will flow. So you will have 5 also. Same things, basically the same physics. So I will not repeat many of them because you can already understand it yourself. Now let me now calculate the current for 1, and that I will use then to explain the rest of the things. So the current for 1 then, let's see whether I can calculate the current this way. J sub T is the net current that's flowing across this junction. I'm not using the drift diffusion theory, right? Previously I used the drift diffusion theory, minority carrier transport and all those. There's no minority carrier here. On the right hand side, full of electrons. On the left hand side, full of electrons also. I do not have any minority carrier, so Schottky barrier is a majority carrier device, right? And so I'll have to calculate it slightly differently, and you can see that there's a discontinuity in the conduction band. Okay, let's look at it. It's very simple. So the blue part is the current flowing from metal to semiconductor at a applied voltage of VA. And the red one is from semiconductor to metal. Now I want to calculate a voltage, applied voltage VA, so I have put a volt V sub A in both cases, A for applied. Now the next one is interesting, because next one doesn't happen in general. The next line says that the metal to semiconductor, the current that's flowing, the blue one, that one, whether you apply a bias or not, doesn't matter. Do you agree with that statement? Because you see what has happened, that although the VBI is moving up and down in response to VA, the charge, the depletion region in the other side, in the metal side, is so tiny that even with bias, it's not going to change much. It's going to stay zero. So the barrier that you see starting from the metal side, metal Fermi level, all the way to the top of the junction, that is independent of bias, going from the metal to the semiconductor side. So therefore, this doesn't depend on voltage. So instead of writing Jm to S, metal to semiconductor at VA, I could just say that thing doesn't change with respect to voltage, and therefore I can set it to voltage equals 0. Same value, that's what I'm saying. Okay? Now, at 0 bias, that's what I want to calculate. So I want to get an expression for what was the current from metal to semiconductor at bias 0. Well, what was the current at 0? The current must have been 0, net current must have been 0 because of the detailed balance, right? Any process that is going from left to right at 0 must be balanced by a separate one going from right to left. As a result, I can say the net current when the voltage is 0 is also 0, and as a result, the net current from metal to semiconductor at equilibrium must have been equal to each other, right? Going from semiconductor to metal. Do you see that? At the voltage 0. That makes sense because at equilibrium, there is no net flux. If there were net flux, the Fermi level couldn't have been flat, right? Fermi level being flat means no current, and no current means the component must balance out each other. So that's what we have, and so I'm almost done. So this is detailed balance, and so what I have here, now you can see the metals to semiconductor at bias 0, I could replace it with semiconductor to metal at bias 0. And so all I have to do is to calculate the current from semiconductor to metal at various biases, and I don't really care about the metal because I have already thrown that away. You see, in both cases the metal is the most important thing, but in some way in depletion region I don't care about how much it depletes because it's tiny, and similarly in here by using detailed balance I have sort of forgotten about the blue region, and only the red I care about. So let's calculate it. It's not difficult. So the metal to semiconductor current is Q, that's the charge, Nm over 2. Now Nm is the number of electrons, which I don't know because it's not like doping or accepted that I know about. So metal I do not know. Divided by 2, why? Because half of them going in the from light to left and the other half is going from the blue. Half of them is going in the positive direction, half in the negative direction. So I only take the half that is going to cross the junction, and so I have that 2. And of course not all those blue electrons will be able to go, only those that have energy above the barrier. Phi sub b is a barrier. Only those that have above the barrier, only those will be able to go. So I have multiplied with exponential of q phi sub b divided by kt. That's the Boltzmann distribution, right? So if his barrier is very high, only then I can do it. If it is very low, then of course I have to do this Fermi-Dirac and other issues that I forget. And then the thermal velocity, the velocity on the average the electrons move. So I put that in. That's from one side. What about the rate side? Now from the rate side, I have Ns divided by 2. N is the number of electrons on the semiconductor side. That I know, right? N is equal to, if it is Nd doped, N is equal to Nd, right? So Ns is equal to Nd, whatever is the doping. In the extrinsic region, if it is in this freeze out or intrinsic region, then I will calculate it accordingly. Do you see that the barrier this time for these red electrons is Q VBI minus VA, and if the electrons have energy above that, only those will go. If it has below that, it can go, but it will be turned back by the mountain, or turned back by the barrier, and so they cannot go and they will not contribute to the current. So I have Q VBI minus VA divided by KT, and thermal velocity once again is the same. Now the two thermal velocity should be the same or not? They cannot be the same, right? Because remember, velocity is half mv squared is equal to kt. And v half m for metal is the effective mass, which is different from the effective mass of the semiconductor. So they are not necessarily the same, but I'm going to forget about the blue one anyway. So I shouldn't have to worry too much about it. Now this one, I have just split it up into two pieces, q VBI and VA over KT. And this in equilibrium must be equal to this. Do you realize why? Because when you set VA equals 0, this quantity is exactly the same as the blue current on the other side, because then these two must be the same. And as a result, I can write it in this particular form. This particular form is essentially J semiconductor to metal at 0 voltage, because let me see whether I explained it properly. In this case, this is the current at non-zero bias, right? At zero bias, this VA should be equal to 0. And in that case, then at zero bias, the metal, because of the detailed balance, metal semiconductor and semiconductor to metal, those two currents must be the same. So if you hide this VA part, you can see this is the metal semiconductor part. And therefore, when you have the applied voltage, you bring back this exponential. And that's the current. So you take that thing out, and do you realize now that from here, I can calculate a current which will be a constant. On the left hand side, there will be a constant, which I do not know a priori, but it will be some sort of constant. And I have phi sub m, and then it goes exponentially well voltage. So if you put a log on the voltage versus current, then also log linear or semi-log, then what slope do you expect? At a few, if VA is a little bit higher than KT, then it's going to be Q over KT, right? And so that's the region 1 that we have discussed before. So it has very same dependencies, but look at this prefactor. The prefactor is not like Ni squared divided by Na and Ni squared divided by Nd. Remember in the PN junction I had that? So the prefactor has changed, but the rest of the things have not changed at all. The same exponential dependence, I have it here. Now what I want you to do is to, when you go home, let me check whether you really, or check for yourself whether you really understood how this calculation was done. I did it for a metal semiconductor junction, right? And I got this result, whatever the result that I just showed you before. Now, if you do it for a PN junction, generally we did it with the minority carrier, electron coming in and in a small signal, things oscillating up and down, and all those things we did. You can get exactly the same result by thinking about as if you have two electrons, two fluxes of electrons, one coming from P to N side, another coming from N to P side. And then for the electrons that are coming from the blue electrons, there is always this variable, VBI minus VA. And then you subtract the flux. You will exactly get back to the PN junction theory or PN junction derivation that you did. So this is slightly different way of doing the same thing that we have done before. But this is in some way more general, because this allows you to calculate current anytime you have a discontinuity. The minority carrier transport and other things that you had cannot directly be applied when you have a strong discontinuity. You have to do some more modification, right? So thermionic emission theory will be useful in this case. By the way, if you look at recent literature of how people handle carbon nanotubes or ballistic transport, you hear about this, the devices are getting so small, electrons goes from one contact to the other without ever scattering. Do you hear about these things? What is the channel length these days of transistors? So they are working on nowadays maybe 22 nanometer. The channel length may be 12 nanometer, 120 angstrom from source to drain. And many times they will not scatter at all. If you calculate the value of lambda, mean free path, do you remember mean free path? If you calculate it, you will see that many times it is becoming comparable or larger than the channel length separation. How do you calculate current? You don't have scattering. If you don't have scattering, how do you talk about mobility and diffusion coefficient, right? Without scattering. But even in that case, if you apply a bias, use the thermionic emission theory, flux is going from right to left, left to right, subtract it, you will get a beautiful answer, no problem. So what you're learning here is, even today, is exactly the same of what people do in their research literature. Okay, so to conclude, I have talked about Schottky barrier diode. It's a majority carrier device. Do you understand why? Because it is always the majority carriers are playing transport, no minority carriers here. Very important distinction. It's a historical importance, but as you said, carbon nanotubes and modern MOSFETs, these are actually treated by the same theory, so it's also relevant now. History repeats itself in some way, interesting ways. There are similarities and differences in PN junction. Similarities in terms of band diagrams and other things, right? Exactly the same. But in terms of calculating current, we use thermionic emission theory. So we should be able to understand this difference and apply them in both ways so that you understand the full power of the method. Now, the trap-assisted current and avalanche breakdown, Zener tunneling, all are the same, exactly the same. I'll show you a little bit in the next class, but exactly very similar to the junction diode. You have a depletion region, well, you have Shockley-Ridgeway recombination, and then you integrate over the junction, you have the same result. So what I'm saying that these two pieces, Schottky barrier and PN junction, read this side by side and read this closely, that why something happens here doesn't happen here. You should be able to clean this up, and once you have done this, then for the rest of the devices, everything, MOSFET, bipolar and all those things are a series of PN junctions, a series of metal semiconductor and PN junction combinations. If you understand this, rest becomes very easy. Okay, thanks.